make a sense. Interfering with the microphone. Test. Okay. I think that'll do. So good morning, everybody. How are you doing today? Well, good. Have you had an opportunity to take a look at assignment 2? No? Anybody? Not really? Okay. Well, so it goes. As long as you look at it soon enough to be able to complete it before the due date, that's all that really matters. So the ongoing developing test situation, I asked bookings, could you pretty please give us the exact same time but a different room? And just one, well no, I said the exact same time, just 1 week delay, please, if that's possible. They said, possible, but only if we split the class across 2 rooms, which I said, yeah, okay. So there's going to be 2 rooms that we're going to write the test in. This should not matter at all, except that you should come to the correct room. Basically, we'll do like, last names A to M, last names N to Z type thing to split the class up. And that's how we're going to do it. And it probably won't matter very much if you go to the wrong room, just as long as everybody doesn't go. Well, actually, if everybody went to the wrong room, it would work out anyways as well. As long as like 50% of the people don't go to the wrong room and end up in the other room, because then we'll have all of the people in one room instead of splitting them. You guys know what I mean. At any rate, so aside from that, I don't think there's anything really to talk about in terms of housekeeping. So, shall we just get right into it then? So, oh, by the way, my lightsaber broke.
Oh, no.
Yeah, press F in the chat for the lightsaber, please. Yeah, I dropped it and it just split open and like just spilled its guts all over the floor. It was very, very visceral and just, yeah. I think it's repairable, but we'll see. I might just have to buy another one, despite the fact the first one was a gift. So now, because like now I'm obligated to have a lightsaber, right? Maybe I'll get a red lightsaber like a bad guy this time. Yeah, like the double-ended lightsaber from the first movie, or the first prequel that nobody liked, although it was actually not as bad as we think it is. Anyway, Star Wars prequel series, underrated. Anyway, let's move on. So, binary heaps then. We've talked about binary heaps quite a bit. We should have a reasonable understanding of the process now. So now we have to talk about, what is the point of all this, and that would be the generation of yet another sorting algorithm. This time we are doing heap sort, right? So I did a demonstration of heap sort before the break, but just so that we're all, on the same page, I'll do it again, and this time I'll try not to mess the math up. So, when presented with an array, if your desire is to perform the heap sort algorithm, obviously this must be organized into a binary heap in order to perform heap sort, right? So, just because it's easier to represent this way, let's take this array and split it into the heap, visually or pictorially, so that we can work with it somewhat more easily. Wait a second. Okay, I've got all of my dice. So, I realize this gets a little messy, but, if you can sort of visualize the lines going between them, then, this starts to fall down, the dice start to fall down a little bit with graphs because you can't see the edges, but, maybe I should get like straws or something. But anyway, so this has been arranged into a binary tree. It's not yet a binary heap because it does not express the binary heap property. What is the binary heap property again, anybody? Oh, come on, it's not that early in the morning.
The child is always less than his parent.
Yes. If you compare the values of any child and parent, the parent must always be greater than or equal to the child. Right? So, taking a look at this is obviously not holding. So, what we do, in order to establish the binary heap property, we must iterate through the various nodes inside of the binary heap, applying the sink or swim procedure. Right? So let's do that quickly now. Let's proceed in the order that things were in the array. Right? So this is going to have to be sink. There we go. Comparing, take the greater, sink it down. There we go. Compare this one. Take a look through here. Sink that. That's fine. This is good. This is, these two are good. Looking at this one, that's good, that's good. Here, we must sink it down, and order is restored. So you can see that despite the fact that we started with an essentially random array, we didn't actually have to make that many swaps to organize this into a binary at any rate. So, I'm going to sort of use this strange aluminum rod as a dividing line now in my programming table. This inside here will be our array representation, right? So remember, one of the features of the data structure that we're working with here, we can consider some elements of the array at the end of the array to not be in the binary heap. They are simply elements sitting at the end of the thing. If you remember, our delete maximum function swaps the maximal element of the binary heap with the one that is in the most extreme position linearly. We then no longer consider that position to be a member of the binary heap. We reduce the heap's size by 1, and we, after the heap section, we increase that size by 1. Right? With me so far? So, heap sort, once you have the basic binary heap operations, heap sort is literally just repeated application of remove maximum, right, or delete maximum. So, as I'm about to demonstrate. So, our maximum, of course, in this case is 6. We swap it with the end element, move that end element into what we consider to be our non-heap section, and then we apply the sinking algorithm, which we have an arbitrary selection here. I had a couple of questions, actually, after the lecture yesterday about what happens in this particular case, actually, so it's worth going through. In this case, we have 2 child nodes which both have the same value. So the question might be, which one do you pick, right? The answer is, it actually doesn't matter. It doesn't matter at all which one of these 2 you pick. If you pick this one, swap that into the top position, then because, and swap that here, because the binary heap property states that child nodes must be greater than or equal to the value of the parent node. These 2 nodes still satisfy the property. because, you know, it's greater than or equal to and not greater than, right? So, and the same holds the other way as well. So it doesn't matter from the perspective of like maintaining the heap property on these three nodes. It doesn't matter which of the two you pick. And it also doesn't matter which of the two you pick with respect to like the comparison of nodes in this branch versus that branch, because we don't compare nodes in this branch versus that branch underneath these two child nodes, right? It doesn't matter. From the perspective of the sync algorithm, the sync algorithm is always going to bring to the top the maximum of the two children, right? So that's over time just going to pull the max values up through the branches appropriately, despite what's going on in these, further extremities. Again, we're kind of in union-find territory to some extent, where it does not matter, like, in union-find, the actual physical connections that the algorithm maintains does not matter at all. All that matters is that when you test for connectedness, you get something correct, right? We're kind of in a similar situation here. We don't care what the relative positions of these values are, relative to left and right branches, because because we're testing as we go down with the sync algorithm, we're going to get the correct result anyway, so it's useless information to keep track of. That being said, once we hit topic 7 and we start talking about binary search trees, it is going to start to matter, right? So for the purposes of searching, that is a property that you need to maintain. But for the purposes of sorting, it doesn't matter because the algorithm still works. Does that make sense? Any questions about that? You can cause yourself a lot of anguish by keeping more information than is necessary to solve your problem. That's a good algorithms course as applied to life rules type result. So, proceeding. Swap maximum. Swap these. This guy is no longer considered to be in the heap. We then examine swap here, because that's the max of 2. Max is this one, swap there. Max is this one, swap there. Heap property established. Maximum. Swap for lowest position. Place outside of heap. Examine. Again, arbitrary decision, doesn't matter which one you pick. Again, arbitrary decision, doesn't matter which one you pick. Typically, in like an actual programming implementation, if there's a tie, you always go left or something like that, right? Just because that's the easiest to program and it literally doesn't matter. So, maximum swap out, or swap here, place outside, examine, swap for maximum, swap for arbitrarily decided arbitrariness. There we go. Take a look. That's a 4. Swap. There we go. Oh, wait a second. I performed a swap I shouldn't have, didn't I?
Yeah.
There we go. I'll undo that far. Sorry, I didn't get a lot of sleep last night. I'm kind of like, it was one of those nights where like, I was like dead certain that my wife was going to go into labor in the middle of the night, because that's often how it happens. So I was kind of a little bit anxious as I was sleeping. But anyway, that's not any of your concern. Yes?
Is there a benefit to swapping out the root node with the bottom and swimming down, as opposed to just taking out the root node and then swimming up the ranks?
Yes. So if you examine it from the perspective of, that's an excellent question, let me repeat it. So the question is, what is the purpose of swapping? Why can't we just remove the maximum and place it somewhere else? Well, in the first case, it makes this an in-place algorithm for sorting, right? Which is advantageous because you don't have to spend any additional memory. That's like a small benefit in some cases, but a benefit nonetheless. If you notice the way in which these nodes have been placed inside of the array, if we are swapping the maximum into the end position of the heap each time, basically we end up with a sorted array for free. Right? We don't have to perform any additional operations to place these nodes in any kind of order that would denote an ascending sort. Does that make sense? So, continuing on, we swap, bing, bang, boom, maximum, arbitrary, maximum, there we go. And this is placed there, swap, place outside, arbitrary again, sync, there we go. Swap maximum, examine, swap for max, swap for max. So you can kind of see how like this is one example where like we have a lot of repeated numbers, but you can see how like the threes kind of get queued up the branches for next selection, right? It's kind of cool, right? Algorithms is a cool class, I enjoyed teaching it. And out, and swap, there we go. And swap, there we go. Arbitrary, swap that again. And swap here, swap these, there we go. And let's just see how I did. There we go. Everything's sorted. Good. So, in general, that's how things go. Now let's see if we can analyze things a little bit, because this class is, 1/3 understanding how things work and 2/3 of being able to analyze how things work. So, yep, we've done that. Yes. The trace, we've already sort of, yeah. So, proposition. Deep sort construction uses less than or equal to, or at most, 2 n comparisons, and at most n exchanges. Also a proposition. Deep sort uses at most 2 n log base 2 n comparisons and exchanges. The algorithm can be improved to approximately 1, but no such variant is known to be practical. So basically, it's kind of one of these things where there are certain optimizations you can perform which sort of invoke the law of diminishing returns. So that's what it means on the slides when it says possible but not recommended. It's possible to perform further optimizations, but in terms of practicality, it's not normally done. It's this, for example, is a good example of a situation where you could, in theory, squeeze a little bit more, squeeze a better worst case runtime out of the thing, but at the cost of making it worse in other ways that just kind of blows out the advantage, right? Make sense? Good. So, the significance of this algorithm is we have an in-place sorting algorithm with an n log n worst case runtime. This is this kind of puts it on the same level, shall we say, as something like quicksort, right? Our bidirectional scan algorithm for quicksort is also an in-place algorithm. But As opposed to quicksort, this isn't a, this isn't necessarily a, divide and conquer recursive algorithm. So despite not being divide and conquer, it's still achieving n log n worst case runtime, which kind of makes it a bit interesting, because normally, if you're seeing a logarithmic runtime, you're either doing something with trees or you're doing something with recursion or both. So, make sense? Hopefully. So quick space requires some extra space. Worst case is quadratic. N log n worst case quicksort is possible but not practical. Heap sort is an improved, and it's, merge sort also requires extra space. So heap sort is an improvement on both merge sort and quicksort in certain respects. Although quicksort's general case runtime will outperform heap sort, its worst case runtime is much worse than heap sort. Heap sort manages to achieve the fabled n log n runtime, worst case runtime, while still being a pretty good algorithm overall. Bottom line is, heap sort is optimal both for time and space, but the inner loop is longer than quicksort's, and it makes poor use of caching. Array entries are rarely compared with nearby array entries, so the number of cache misses is far higher for quicksort, merge sort, where most comparisons are with nearby entries. So this is kind of like a more advanced operating system type issue, right? Because you're comparing things that are sort of more widely dispersed and not, like merge sort. If you take, for example, merge sort, in theory, you perform multiple consecutive comparisons with the same number, right? That means that generally it only has to be loaded into register memory once, right? And it's held in register memory for as long as it's needed for comparison, at which point it's thrown away again. That seems like a small thing, but keep in mind that using a value which is stored in register memory takes approximately 1/3 of the time that it takes to fetch and load from an external memory source, even if that memory source is quite fast, right? Because, and you kind of have to have some knowledge of assembly programming to know this, but in assembly programming, which, maybe those of you who took 1FC3 with me over the summer have some vague awareness of this, but the CPU has instructions for loading from and unloading to, shall we say, external memory, right? If, like, your array is too large to be stored in register memory, obviously register memory is typically only 16 registers for most CPUs, actually. 16 and no more than 32. So that means that to load from memory and execute and then put back takes 3 times the amount of time it does to just operate on something you already have in register memory. So if you're doing a lot of comparisons with things that you have previously compared with, then you can sort of squeeze that degree of optimization out of it as well, which is something merge sort can do, but not so much with heap sort. But that's kind of a very, very small technical point. And these types of register level optimizations aren't going to be useful most of the time unless you're an assembly programmer. Anybody here an assembly programmer?
We have to be for our other course.
Oh yeah? You're taking assembly for another course?
It's 2GA3, it's computer architecture.
2GA3. All right, well, have fun with that course. Honestly, personally, I find the lowest level architectural details to be very interesting, But then again, I'm from a mechatronics background, and like the thing about a mechatronics major is that they could, in theory, build a robot from scratch, including all of the electronics and software and everything, given enough time and resources. And by enough time, I mean like probably several thousand years, because that's how long it would take to, do everything, because division of labor is king. But yeah, Marxists are wrong. Division of labor is good. But anyway, so just a couple of quick epilogue points on sorting before we close off the chapter. So this was actually a point that was brought up by one of your colleagues at some point. We have a concept of sort stability. One of the things that you have to be aware of with sorting algorithms is that some will scramble the relative positions of numbers with the same values and some won't, right? So if the position relative to objects with the same sorting index is important, then you want to use some algorithms and not others, right? So this is generally known as the property of stability as applied to sorting algorithms. So a stable sort will maintain the position of elements it will maintain the relative position of these elements that have the same key, and an unstable sort will not. So stable sorts include insertion sort and merge sort. Unstable sorts include selection sort, shell sort, quick sort, and heap sort. So you can see that, again, there is a reason that we've covered 6 different sorting algorithms in this class, and not just said, quick sort is good enough, and that's the only sorting algorithm you'll ever need to know. It's not true. Everything is situationally dependent. Each sorting algorithm is a tool in your tool belt, and the master of the craft knows how to apply the correct tool to the correct situation, right? Good. So, quick summary of sorting algorithms. If you want a quick summary, there we go. Any questions about sorting algorithms at all in general? Yes?
Regarding to the in-place sorting, regarding to the heap sort, you mentioned that we got the final result for free after swapping from the maximum to the bottom. What's the implementation for that? Why we got that free, the final result free?
It's, okay, so the question is, I mentioned that we get a sorted linear array for free once we have performed all of the swaps or performed all of the delete maximum operations. So if I could clarify that a little bit. It all has to do with the fact that we're storing things in a linear data structure to begin with, right? So I'll just do a small example, right? So, thank you. So the way that I was representing this was, let me just establish the heap property here. Here we go. The way that I was representing this was in tree representation. But it's also important, to also hold in your mind that that's not actually how the computer is keeping this data. It's keeping the data linearly, right? In an array that kind of looks like this, right? So we access these indexes by doubling the index that we want to access the children of, or doubling and adding 1, and dividing and taking the floor, right? So What the swap operation looks like on a linear array will probably tell the tale, right? So, and I'm going to create these divisions in the array just because I think that's useful. So, the first if we were to perform heap sort on this very small array, we swap this into the most extreme position. We then consider that to be no longer in the binary heap, right? And then we perform the sinking algorithm. Sink down, and that's fine, right? Then we swap the maximum again. That's no longer in the heap. We examine, it's all the ones. So nothing need to be done. You know, swap again, place that there, right? Nothing need to be done. Swap again, place that there, nothing need to be done. Finally, sorted array, right? So the reason that you get it for free, you get a sorted array for free after performing repeated, like deletion of all items, is because you're placing them back into the array at the end in the order of decreasing value that is raised up by the sinking process. Yes.
But after you put the at the end, it's n minus minus. It's literally out of that array list.
So yes and no. We are not decreasing the size of the array. We're not performing a dynamic boundary allocation to shrink the array itself.
Oh.
There we go. Yeah, that's actually a very important point. Thank you for bringing that up. So when I say we remove it from the heap, I do not mean we make the size of the array that stores the heap smaller. That's not what we're doing. What we're doing is we're drawing an intellectual barrier at some point in an existing data structure saying that this half is the heap, this half is non-heap elements, right? And we're increasing the number of non-heap elements every time we decrease the size of the heap by one element respectively, and that's why, by the end, the non-heap elements have grown to include all of the elements, and they happen to be sorted when we're finished. Make sense? Excellent. Wonderful question.
If we try to do heap sort with a linked list, why would it be more difficult? Can you please explain?
If we tried to do heap sort with a linked list, why would it be more difficult? Well, so with respect to a linked list, the establishment of a binary heap itself is not, it's not going to take any more time, right? Essentially what we've done is we've baked a kind of linking structure into the array indices by having our formulas to calculate child and parent nodes, right? So with respect to the sink and swim operation, the linked list does not pose any detriment in that respect, right? However, did I make this an assignment question?
I don't know. I haven't looked at assignment yet.
Yeah. Let me just look at the assignment, because I don't want to give away the entire assignment. It is, isn't it? That's why everybody's giggling. You just about tricked me. It might be a tutorial. Let's see. Yeah, that is an assignment question. All right, figure it out. Sorry, but you guys got to think about that one. I'm not just going to give you the answer in the lecture. It's not one of those what do you think this is, a biology class? Yeah.
For the heap sort, if we perform it on a random list, we can't necessarily assume that random list is adheres to the heap principle, right?
Certainly not, yes.
So we would have to so if it doesn't adhere to the heap principle, then we would have to make it adhere to the heap principle. So
Mhm.
then, wouldn't it add to the n log n time complexity?
That's an excellent question. Doesn't establishment of the binary heap property add to our time complexity? So here's the question. How many items do we need to arrange into the binary heap? N. How long does it take to arrange a single item using the sync or sort algorithm?
At most log n
At most log n. So the complexity would be
of n log n.
n log n. So we are contributing not to we are not increasing the big O, we're increasing the constant,
So
right?
2.
Yeah, so the worst case complexity will remain the same. You know, that being said, you do have to arrange it into the binary beforehand, obviously, and that takes a certain amount of time, but it does not increase the complexity. Any other questions? Okay. Okay, good. We are finished with sorting algorithms. We now have covered as much sorting as it is reasonable to cover, and the second year level of the computer science program, shall we say. Obviously, okay. Let me see. Do I have it now? Let me see. Because there's like I found a cool website that performs sorting algorithms, and I just wanted to show you that because it's a very cool visualization before we go on to topic 7, if I can manage to get some, you know. Cool. Great. Sort visualizer.com. So, for example, if you wanted to see the one we just talked about, heap sort.
Does it have audio?
Does it have audio? I don't know. Maybe. And ramp up the elements to a lot. But that will take some time, so let's just do it. Okay. So, establishment of the heap sort property. And there you go. Now it's pulling out maximum, sinking down. Right? Very cool.
Do you usually have audio? There's a whole YouTube channel that
Yeah, it does slightly have audio. Okay. In a very cursory fashion, it has audio. So,
what is big
what is what?
pancake?
Pancake sort, I don't know. And you also have weird sorts. Okay, there's only one of these other sorting algorithms that I have any familiarity or awareness of, and that's radix sort. Radix sort is kind of an interesting one. It was it's a sort that was developed as a punch card algorithm for very, very old computers that ran on punch cards. Basically, it's a digit by digit sort. So you sort by the first digit of the number, then by the second digit of the number, because digits were often represented by holes in punch cards. So radix sort basically nobody uses anymore because it's not efficient and only applies to computers that don't exist anymore. So yeah, but if you're interested, then you can do your sort as well. But anyway, good. So wonderful. Moving right along. So, if 30% of all computing cycles in the past were spent sorting data, 25% of computing cycles in the past were spent searching for data, and probably the degree to which searching has become more important in the age of the internet and big data has become, it's more and more important increasingly as things go on. So we're going to talk about searching algorithms now. We're going to talk particularly about symbol tables and binary search trees. We're not going to talk about linear search. You're assumed to know how linear search works. We are also not going to talk about binary search as applied to a linear array. You should already know how binary search works if you took 1MD3, right? Because we covered that in 1MD3. We're going to start off at level 2 and leave the level 1 stuff for the firsties. So, symbol tables. What the heck is he talking about now? A symbol table is a data structure for key value pairs that supports 2 operations: insertion of a new pair into the table and search for a value associated with a given key. Roughly speaking, we are talking about dictionaries in Python. So, or at least, we're going to take dictionaries in Python, show you how they're actually supposed to be done so as to have good runtime. Because the dictionaries in Python have a key flaw, which we shall be exposing over the course of the coming lectures. So, yes?
How is this different than hash table?
Hash tables are different. We'll be coming to them later on. The difference between a symbol table and a hash table, roughly speaking, is the hash function. Symbol tables don't have a hash function. So, but I'll feel more confident answering that question once I've studied the hash table material that I'm going to present in a couple of weeks. Okay? So please hold questions about hash tables for when we're talking about hash tables. So, symbol tables are generalized arrays. Keys need not be between 0 and n-1. You will find that in the examples in the slides, we're often using numbers anyways. As is often the case in this class, numbers are like the natural numbers or the characters that they use in the traces are a stand-in for any kind of orderable data type. That is that's the big thing, is that with the symbol table, is that the keys themselves need to have some kind of ordering relation that you can apply. So, it turns out to be extremely useful to be able to map 2 different domains together. You guys, I hope, have discussed relations in any of your various formal logic mathematics courses. Discrete math, you've talked about functions and relations, all right? The dictionary, or the symbol table, is the implementation of a relation inside of a computer system with certain, caveats. Number 1, you can't have duplicate keys, right? But at any rate. So, numerous languages support take symbol tables either as external libraries, built-in libraries, or built into the language itself, such as with snake language. So, it's like the applications of these things are almost unbounded. DNS lookup, your key would be the domain name and your value is the IP address. An actual dictionary where you're, storing definitions of words. What a dictionary is it's a mapping between words in a language and more words in the language which describe that word in the language, right? So it's like a one-to-many relation with an ordering on the words in the set that you're mapping to. Terrible way to define it. I'm sorry, I'm just amusing myself at this point. Compilers need to be able to map variables to data types, for instance, for the purposes of writing a type checker. Good. So, we sometimes also call these associative arrays. This, roughly speaking, is our interface if implemented as a Python class. So, most particularly, we are interested in the put and get methods, which add in a new key value pair to the symbol table, and which retrieve the value of a particular key from the symbol table, respectively. Basically, the rest of these are kind of your normal add-ons that you would normally have. Removal is slightly interesting. Is empty size not terribly interesting. Contains is just get but doesn't return the value. Right? Make sense? Good. So, oh, and keys, just, you just trace through and gather all the keys in the dictionary. So, symbol table conventions adopted by the textbook. These are not necessarily going to be universally applied to symbol tables in general. These are the types of things that may form design decisions on the part of the library or programming language which is being used to implement the symbol table. In general, neither keys nor values are permitted to be null. So we're already departing from Python because Python will allow values in a dictionary to be non-literals, right? The method get returns null if a key is not present. The method put overrides old values with a new value. That, incidentally, is how Python works. Intended consequences of value not equaling null. It makes it easy to implement contains. Again, contains is just the get method, but rather than return the thing that you might find, you test to see if it's null or not and return the Boolean result of that. Further, it allows a lazy version of delete. So, rather than, actually freeing the memory that has been associated with a particular key, it allows for a more lazy approach to deletion, which permits you to just overwrite the value of that particular key value pair with null, and then it's, no longer in the dictionary, theoretically, although physically it is still in the declared memory, right? What would be an advantage of this? What's an advantage of the lazy approach to deletion? Yeah, if you want to reinstantiate it, you don't have to do any dynamic memory allocation, right? You don't have to declare new memory. If you imagine a scenario where keys like pairs are being rapidly added and deleted, right? Like if addition and insertion and deletion happens very frequently, the lazy approach to deletion, it saves you time further down the road on insertion operations by not having to declare the memory again. Cool. Any questions? Well, in that case, congratulations on almost tricking me into answering one of the assignment questions.